So before we get started making our slope field for this, we'll talk real briefly once again, just to make sure we are sure we know what slope fields are doing. So a slope field, when we make a slope field, we are taking the derivative and remembering that the derivative is the slope of the tangent line to y. And we're using those little tiny line segments that we drew of different slopes to model the behavior of y on a small scale. We're using the idea that of linearization, that the tangent line represents the actual function on a small scale. And so that's what we're doing. So we're plugging in different points. You know, we did all the x values and 0 and all the x values of 1 and all the x values of 2 when we were doing these other ones that only had x in them, cosine x and root x squared minus x plus 1. But now, since we have an x and a y, we're going to have to take into account both x points and y points. And generally, when you do this on the AP test, what they do is they give you like this grid of points. And they'll say to sketch the slope field at the given points. And so that's exactly what we're going to do here. So I'm going to give you this. I don't like that. I could have just used an array. So we're just going to go 2 points out in each direction. Usually they don't give you nearly as many as I just tried to put up there. So we'll go out to -2 and to +2 in both the x and the y direction. Nice little square here. And so we're going to sketch the solution to dy dx equals x minus y at these 25 points. So anytime they give you a differential equation is equal to x plus or minus y, or something like that, 2x plus y, or 3x minus 2y, some product or sum of x and y. What you want to do is start off by just setting dy dx equal to 0. So if dy dx equals 0, that tells you that x minus y equals 0, which in turn tells you that y equals x. Everybody agree with that?
Yes.
Good. Where's that line? Sort of. That's the line y equals x, right?
Yes.
Every point on that line, the x value is equal to the y value. So at every point on that line, I need to draw a line with a slope of 0. And that was supposed to be horizontal, but it wasn't. That's better. So those are all the points on the line y equals x, and I've drawn them all with a slope of 0. Everybody good with that?
Yeah.
All right. So now we'll do the same thing with dy dx equals 1. What does that tell us? We don't need to write. We know that x minus y equals 1, which tells us that y equals what?
X minus 1.
Exactly, which is this line down here, sort of, if I'd drawn it better. And so those will all have a slope of 1. And what's going to happen if I choose dy dx equals 2, do you think? We should get y equals x minus 2. And so a slope of 2, so a little steeper at x minus 2. And it's going to continue a little steeper at x minus 3 and a little steeper at x minus 4. Good or no?
Good.
All right. And what about for dy dx equals -1? What equation is that going to give us?
X plus 1.
Exactly. And so at x plus 1, this line, all the slopes should be negative. Good. And what about -2? Should just keep moving in the opposite direction, right? Y equals now x plus 2. So a little steeper negative, and then a little steeper, and then a little steeper. And that should give us the basic idea of what a solution to this might look like going through any particular point that I might choose. So let's say we chose the point 0, 1. Well, it should have a slope of 1 there, should flatten out, and then increase to this slope of 1 over here. And over here, it should go to the left and get steeper. And something that we'll want to note is along this line, y equals x minus 1, all the lines have a slope of 1. So the slopes are 1, and the slope of the line that they lie across is also 1, which means this is going to give us an oblique asymptote here, or a slant asymptote if you prefer. So the lines are a slope of 1, and they lie across a line of slope 1. So this will never actually hit this slope of 1. It will just approach it eventually. And so if I picked some point that might have been below here, like this point, it should increase up to that asymptote also, and then get steeper as we go down. And so depending on what point I chose for us to sketch it through, if I said sketch it through 0, 1, it should look like this. If I said sketch it through 1, -1, it should look like that. So good or no?
Excellent.
Wonderful. Any questions on that?
So for the oblique asymptote, so you know something is like a slant asymptote when the mini slopes match the big slope, like that always happens when
Correct.
that happens?
Yep.
Okay.
That is correct. Yep. All right. Let's try another one. Now this one's a very fun and exciting and special one. dy dx equals x over 2y. So this one is not a product or not a product. It's not a sum or a difference of x and y. It's a quotient, and these ones fall into a category of being either a product or a quotient of a function x and y. So we're gonna do the same sort of thing. I'm gonna give you guys a bunch of points to sketch this at, and we're gonna just do the same 20, well, almost 25 points. We're just gonna do the same 24 points this time. So I'm gonna leave out the point in the middle. Why am I leaving out the point in the middle there at 0, 0?
Because
Indeterminate.
It makes it indeterminate. And anytime your derivative is indeterminate, you're not going to be able to put a point on the slope field there. Derivative being indeterminate means that your function doesn't actually exist at that point. And we'll actually see why that is a little bit later on. Everybody got their little points drawn and ready to do this?
I'm ready.
Okay, so first thing we'll normally do when we're given a product or a quotient of x and y is say, what makes this 0? And we did that earlier with the last one, right? But what makes this 0? It makes it 0 if x is 0, but y is not 0, right? So we'll That was supposed to be horizontal that I failed. That was supposed to be on the point that I failed. All those where x is 0, but y is not 0. And then we'll want to look what makes dy dx undefined. That'd be if y equals 0, but x is not 0. So those 4 points. Good there or no?
Good.
Cool. All right. Then we'll just choose some values like 1, 1. Plug in 1, 1. What do you get?
One half.
Get half. So draw a slope of a half. Plug in 2, 1. What do you get?
1.
1. And you'll note that this pattern of as we go to the right in the first quadrant, they increase should follow for all the rest of them. If I plug in 1, 2, what do I get? I get a fourth, right? Even less steep. And then if I were to plug in 2, 2, that'd be a half. So it's increasing, but it's still pretty shallow of a slope there. And anytime we have this quotient or this product of them, we should be able to mirror this in both the second and the fourth quadrants. We should be able to mirror whatever we got in the first quadrant. So if I mirror this down here into the fourth quadrant, I should have a negative a half and a negative 1 and a negative 1/4 and a negative 1/2. And if I mirror it over here, I should end up with the same things, right? And I know my slopes aren't all perfect there, but they're generally close enough. And then we should be able to mirror the second quadrant into the third quadrant here. So these ones will be positive slopes. And that's our slope field. And so suppose I said, take the point through 0, 1. Well, it should be flat and it should slowly start to curve up. So somebody asked a question, how come you can mirror the slope? So imagine if I've got a positive x and a positive y, I'm going to have all positive slopes in here. But the numerical value shouldn't change. If I flip it down here, all that changes is the y value becomes negative. So the x will stay the same and the y will become negative. So rather than being positives, these will just be the same, but negatives. And same over here. The x's are the x's are changing from positive to negative, but the y's are staying the same. So the numeric value of dy dx just flips signs. And so we can mirror it in the second quadrant also. And then again, once more, these ones already have negative values. I throw an extra negative in, they become positive, but the absolute value of them, the numeric value of it doesn't actually change. Does that make sense to everybody? Okay, cool. Now, important part of this is that I might ask you to sketch one that went through, let's say, I don't know, let's say this point right here. And so it should come down to being vertical and go up like this. And it could then continue down this way. But we will never sketch down here if we already have a piece up here, because that doesn't pass the vertical line test. And so when we sketch the solution, right, your solution curve to a differential equation, the rules say must, I put a comma there, must be a function. So if I wanted to go through this point, I'd go up to here and continue up that direction, but I would not continue down this way because that would make it not a function. Okay, so good or no?
Wait, why would you choose to go up instead of going down? Is it just like convention?
Well, if I went, yeah, I mean, yes, if I'm above the x-axis or above where they're vertical, we'd go up. And if I'm below where they're vertical, I would go down. that answer your question?
Yeah.
Okay, cool. Any questions on that? Are everybody good? All right, we're going to do a little something extra with this now. dy dx equals x over 2y is what we had, right? So this is going to be the first of what we call separable differential equations. And a separable differential equation is one where you have a product or a quotient of x and y. And these ones we should be able to explicitly solve for y. The way we do it is we do what's called separating the variables. That's why they're called separable differential equations. So we're going to take the 2y and we're going to multiply both sides by 2y so that the 2y is gone from the right and we have it on the left. And then we're going to multiply both sides by dx so that on the left-hand side, we are just left with 2y dy. So everything that has a y in it and the dy. And on the right-hand side, we'll have everything that has an x in it and the dx. Good or no?
Good.
Okay. And so now what we'll be able to do is we'll be able to just integrate the left side and integrate the right side, because if I do something to one side, I have to do it to the other side. And then I will be able to solve for y. So what's the integral of 2y dy?
Y squared plus c.
Y squared plus a constant. And I'm going to have a constant on this side too, so bear with me here for a second. I'm going to write y squared plus constant 1. And on the right, what am I going to have?
X squared over 2 plus constant.
Yeah, plus constant 2. Now, normally when we do these separable differential equations, we don't write constant 1 and we don't write constant 2. Because I could rewrite this like this, right? Y squared equals x squared over 2 plus constant 2 minus constant 1. Well, what's constant 2 minus constant 1?
Another constant.
It's just some constant, right? So normally the standard convention here is that we just put plus c on the side with the x's. And that's what I'll expect you guys to do from now. So we've got y squared equals x squared over 2 plus some constant. And if we were to solve that, we would end up with y equals plus or minus the square root of x squared over 2 plus, like I said, some constant. And we don't know what that constant is because we weren't given an initial condition. But that's the whole idea of a separable differential equation, is to be able to separate it out and solve explicitly for y. And we will do these where we're given an initial condition that we have to actually find that constant. But for this one, we didn't have one. Does that make sense, what we did there?
Yep.
Good. And we're going to do a bunch more of these. But before we do a bunch more of these, I'd like to take a look at the graph of this. Because it should look like our slope field did, shouldn't it? Here's x squared over 2 plus some constant. How about a constant of 3? Doesn't that look pretty similar to what we sketched when we sketched the one that went through like 0, 1 or something? I know that doesn't go through 0, 1, but I guess I could put in plus 1 and then it will. But that looks very similar to what we sketched, doesn't it?
Yes.
Yeah. And how would we get one that was below? Well, we just throw a negative in there. Right? So if we wanted to sketch one that was below, we'd throw the negative in and it would look like this. And we could even get the ones that we had that were out on the sides by throwing in making the constant a negative constant. We get something like this. And it shows two different sides of it, but based on our slope field, we only just draw one side of it. And if I put the negative out in front of it again, it would flip it to be the bottom pieces. Good or no? We see how this is related to the slope field that we drew for this differential equation. Hopefully. Any questions on that? All right, I will give you a minute or so to look at this, read through this. This is the idea of what we just did. This is kind of like the formal, like what you do with a separable differential equation. So I'll give you a second to read this and write it down. And then we're going to practice doing a few more of these where we actually have initial conditions and have to find our constants and find the intervals of validity and all that stuff. Sound good? So take a second, read that, write it down, and then we'll do a few more problems. All right, are we ready? It all makes sense. You get the y's on one side, you get the x's on the dx on the other side, you anti-differentiate both sides and solve for y. Pretty straightforward? Or no?
Yeah.
All right. Let's take a look here at dy dx equals x times y squared with y equal to 1 when x is equal to 1. What do you think we should do first? Probably apply that squared to both the x and the y.
Yes.
And then we'll separate the variables. So we'll have dy over y squared equals x squared dx. Everybody good with that? Multiplied by the dx divided by the y squared. And then we'll integrate both sides. Now, in this particular integral, a lot of people tend to screw this up because they're like, oh, it's dy over y squared, and think that's natural log absolute value y squared. It is not that. Okay, it is the integral of y to the -2 dy. Right? And how do you integrate that? You just use the
Power rule.
You just use the power rule. So what does that become?
-1 over y.
-1 over y. And on the right-hand side, we end up with x cubed over 3. And we'll just put the constant only on the right-hand side. Okay. Good or no?
Good.
All right. So now, some teachers will say solve for y and then find your constant. But I think it's easier to find your constant right away. So if we plug in 1 for y, that should give us -1. And if we plug in 1 for x, that should give us 1/3 plus c, giving us c equals what? -4/3? Everybody good with that? So we should have -1 over y equals x cubed over 3 minus 4/3. And we're going to need to divide everything by a -1 and take a reciprocal of both sides. And one thing I want to caution you about, because a lot of people have screwed these things up in the past with the reciprocals, you need to combine the two fractions together into one before you can take the reciprocal. Sometimes people will like just, suppose this was like x over 2 minus 1/3. You can't take the reciprocal of that to get 2 over x minus 3. People screw that up all the time. And you have to get a common denominator and combine them together to get your reciprocal. Okay. And we also need to divide by a -1 or multiply by a -1. So let's write this as 1 over y equals negative x cubed minus 4 over 3. And now, since we have a singular fraction over here, we can take the reciprocal. We get -3 over x cubed minus 4. Good or no? Everybody okay with that or not?
Good.
Yep.
All right. What do we still need to do though? What's wrong with it?
That isn't y.
What? Say that again?
No, I'm stupid. I was looking at the wrong thing. I'm
Oh.
sorry.
Okay. What's wrong with this x cubed minus 4 in the denominator? We know that x cubed minus 4 cannot equal 0, which means that x cubed can't be 4, which means that x can't be the cube root of 4, right? We have a discontinuity in this. And so the domain of this whole function should be -infinity to the cube root of 4 union cube root of 4 to infinity, but we only pick the single piece that includes x equals 1. Right? And so x equals 1 falls between -infinity and the cube root of 4. So we'll say this is for -infinity to the cube root of 4. We still have to worry about the interval of validity for the separable ones. Good or no?
Good.
All right. And another sort of cool thing to note here is that if we were to take the derivative, and we're going to do this right now, if we were to take the derivative of -3 over x cubed minus 4, we should get x squared y squared. And so I'd like to show that that's the case. So y equals -3 over x cubed minus 4. What's the nice easy rule to find that derivative? Should use the reciprocal rule, shouldn't we? Okay. Reciprocal rule says, first off, negative, so the negative will go away. Keep the constant. Derivative of this, derivative of your denominator, which was 3x squared, over your denominator squared. Right? That's using the reciprocal rule, which we should know, right? The reciprocal rule. And if we look at that, does that equal x squared y squared? Well, first off, x squared is just x squared. So there's that. And y squared would be 9 over x cubed minus 4 squared. And we've got 3 times 3, which is the 9. And we've got x cubed minus 4 squared. So we definitely have that, don't we? We all see that or no? Cool. All right, let's do another one. Give me 1 second here. Sorry about that. All right, so what do we need to do with this first?
Separate.
Separate it. So we'll divide by the y, giving us dy over y, and we'll multiply by the dx, giving us dx over x. And we'll integrate both sides. And if we integrate both sides, what do we get?
Natural log of y is equal to natural log of absolute value of y equals natural log of absolute value of x.
Plus our constant. And so first off, very important when you are solving separable differential equations, as soon as you integrate, I know I said as soon as you integrate, find your constant, but also as soon as you integrate, look for any domain restrictions. They may disappear as you solve for y, but you still have to include them. Anything that you get along the way between as soon as you've integrated and your final y equals, you have to keep those domain restrictions. So x cannot be 0 because we cannot take the natural log of 0. X can be negative because we're taking the absolute value of this x and then taking the natural log, so that's okay. But you have to keep this domain restriction of x can't be 0 in mind the whole time we're working through this. Good?
Good.
Okay, so now we'll plug in our 2 for y and our 2 for x. And what do we get as our constant?
Zero.
Should get 0. Okay, and so we just end up now with natural log absolute value y equals natural log absolute value x. And how do we clear the natural logs off of each side? We exponentiate them, right? We make them as powers of e, which turns this into absolute value of y equals absolute value of x. And we can clear off both the absolute values with plus or minuses, right? So we could turn this into like a plus or minus y equals plus or minus x, which really effectively just becomes y equals plus or minus x. But which do we want? Do we want the plus or do we want the minus x based on our initial condition? Y needs to be equal to x or negative x?
X.
X. And we have the restriction that x can't be 0. X can't be 0 says negative infinity to 0, 0 to infinity is our domain. And which of those, we remember we only pick the one piece that includes x equals 2. So which single piece includes x equals 2? The piece from 0 to infinity. questions on that? All right, we're going to do one more today, and then we'll save a couple for next time. So one more today. You guys want to give this one a try to start with on your own?
Sounds very fun.
Yeah, it should be. All right, I'll give you guys a couple minutes here, maybe 3 or 4 minutes to try and get through this one. Ready, go. All right, so first off, we separated the variables to get dy over y plus 5 and x plus 2 dx. And we integrated both sides, and the right-hand side was really easy. The left-hand side, integral of dy over y plus 5, we had to do u equals y plus 5. And du was dy. We had to do a little bit of a u sub here just to make sure that since this is a function in the denominator, that it could just become natural log absolute value of that. And since du equaled dy, it became the integral of du over u. And so that was okay. It became natural log absolute value u, or natural log absolute value y plus 5, equals x squared over 2 plus 2x plus c. We plugged in 1 for y to get natural log of 6. Equals 0 plus 0 plus c, so our constant was natural log of 6. Everybody agree with that?
Yes.
Perfect. All right. And give us a new page here. So we had natural log absolute value y plus 5 was equal to x squared over 2 plus 2x plus ln 6, right? And in order to solve that for y, we have to exponentiate both sides, which on the left gives us absolute value y plus 5. But on the right, we should be able to simplify this down a bit. One thing that you should always do if you've got e to a power of a bunch of things added together, and one of those things is just the natural log of some number, or in fact, if it's natural log of anything, separate the ones that are not a natural log and multiply that by the other one. Right? This is just exponent rule, right? If I have x to the x to the a plus b, that's x to the a times x to the b, right? That's how exponent rules work, right? So I have e to the a plus b plus c. I can make that e to the a plus b times e to the c. Everybody see that? And why might we want to do that? Well, because what's e to the natural log of 6?
6.
6. So we have 6e to the x squared over 2 plus 2x. And to clear off the absolute value, we'll need to throw a plus or minus in there. And we're going to eventually have to choose one of the other, the plus or the minus. And we can do that at the end if we want. Y equals -5 plus or minus 6e to the x squared over 2 plus 2x, right? And so how do we determine if we want the plus or the minus?
Look at your given points.
Right, our initial given condition was y is 1 when x is 0, right? So if x is 0, e to the 0 plus 0, that's just e to the 0, which is 1. So I've got -5 plus or minus 6 needs to give me 1. Well, -5 plus 6 gives me 1. -5 minus 6 does not give me 1. So we'll choose this. And if we look at our final value here, x squared over 2, we can do that to any x value, and we can add 2x to any x value. We can multiply, or we can make any number that we get up here, e to that power, and we can take that number and multiply it by 6, and we can do -5 plus any number. So no restrictions from that. And there were no restrictions from anywhere along the way as we went through here. If we look right after we integrated, we could have plugged any x value in here, Could have plugged any x value in here, any x value in there. All along the way, no restrictions. So we could say it's good for negative infinity to infinity if we wanted to. And that is our final solution to that differential equation. Good or no?
Good.
Cool. Any questions on that or any of the other ones that we've done today? We're gonna finish up right there with that. We're gonna stop there.